Hey class, it's Mr. Offset here with lesson 9 of unit 5, the actual last lesson of the unit, orbiting systems. So this is kind of bringing everything together, combining uniform circular motion with gravitation into one neat, all connected idea. So the truth is, we know that planets and satellites orbit in elliptical orbits, but we're going to simplify this into a perfect circle so that we can bring in our ideas of uniform circular motion. So this is a simplification that we're making. It's not 100% accurate, but it's close enough for our purposes. So when we're looking at an orbiting system, we're going to think about the dynamics of an object in orbit. So first we have Newton's first law, right? The idea of inertia. So an object in motion wants to stay in motion in a straight line. So the satellite wants to continue at this constant velocity, but it also wants to continue in a straight line tangent to the circle, right? That would be that velocity vector there. So that's what the satellite wants to do at this exact moment. But Newton's second law, right? Unbalanced forces producing an acceleration. We actually do have this centripetal acceleration, and that's resulting from the only force acting on our satellite, the force of gravity, produced because we have a gravitational field, which we just looked at last lesson, created by the Earth, and we have this second mass within that field that's experiencing this force of gravity. So, in actuality, any object that is orbiting is in constant free fall. We talked about last lesson how when the only force acting on an object is force of gravity, we call it an object in free fall. And since here the only force is the force of gravity, our satellite is technically in free fall. Because it's falling because, it's falling, but it's never going to hit the Earth because of the curvature of the Earth, right? The Earth is round, so it'll try to fall into the Earth, but it will never actually get closer to the Earth because of that curvature and that uniform circular motion. So I'll just give you a little visualization of that. So here, imagine the red line is the surface of the Earth, and we're shooting, let's say, a bullet from a gun, and at a certain horizontal speed, right, it would travel and come and hit the Earth. But as I play this little clip for you, you'll see that the faster the bullet goes, the further it's going to travel, right? So as time progresses in this clip, we're going faster and faster with our initial trajectory launch velocity. So here we're shooting the bullet super fast, right? It's probably traveling here, almost 80,000 kilometers. And we continue to speed it up until, right, we're shooting this across the continent, right, maybe even across the Atlantic Ocean. And here we see the curvature of the Earth, and our bullet is landing super far away because we're launching it at a super high velocity. And eventually, there's kind of that split second. It's really short here. Let me see if I can slow it down for you. We got that instant moment where it's no longer hitting the surface of the Earth, right? It's not hitting down across at the equator somewhere near Mexico, but it's breaking away out back into orbit, right? So if it has enough launch velocity, you could technically put this bullet into orbit, right? There it's in its perfect circular orbit, and if you shoot it even faster, right, it's going to form that ellipse orbit, and there's the sun, or our Earth. And if you go even fast enough, right, it's going to spiral out, or it could just break straight away from the force of gravity on the Earth. Right, so the main kind of conceptual part is we are falling constantly towards the Earth, but at a certain point, we'll never actually hit the Earth. We'll continue falling, but never hit the Earth because of that launch velocity. So that speed of something in orbit has to be great enough that it will never actually spiral into the Earth, right? And in order to find that orbital speed, we can use our Newton's second law, force equals mass times acceleration, where the force is the force of gravity, that's the only one acting on it, and the acceleration is centripetal acceleration, which is only changing the direction of our velocity, not the magnitude. It's traveling with a constant speed, constant orbital speed. So as we break open or expand our force of gravity into the universal gravity equation and our centripetal acceleration into its orbital speed and radius, we end up with this equation, right? And you can see that mass 2 will actually cancel out there. And if we were trying to find the orbital speed, again, instead of centripetal acceleration is equal to v squared over r, we're using our alternative 4 pi squared r over t squared. So we can use these two systems of equations to solve for a multitude of problems, combining two equations that we already know, right? Our universal gravitation equation, mass times our centripetal acceleration equation, or this other centripetal acceleration equation. So we got to keep in mind that much like any projectile, it's falling at the acceleration due to gravity, right? Acceleration due to gravity. But we don't have gravity of 9.81 unless we're right at the surface of the Earth. If we're shooting a bullet right at the surface of the Earth, then you could arguably assume that we're using 9.81. But we're often working with satellites that are far from the Earth's surface, so that R value is bigger than just the radius of the Earth. Therefore, we're going to have a weaker gravitational field and a smaller gravitational acceleration value. Any object in orbit is in free fall, right? So they are weightless, there's no normal force. Right? This idea of your apparent weight being equal to your normal force. If your apparent weight is 0, your normal force is 0. There's no surfaces in contact with this, right? It's only the force of gravity acting over a distance. And since normal force is all about surfaces in contact, we have no weight, no normal force. Here's a fancy astronomy word. We got geosynchronous satellite, a satellite that remains directly above one location on the Earth. So it has the same period of orbit as the Earth's rotation. Here is our one and only example for the day. We want to determine the orbit speed of a satellite that is 750 kilometers above the surface of the Earth. So we have our Earth. There's the center of the Earth. We know that our satellite here, there's a nice satellite picture, is at a distance of 750 kilometers above the Earth, right? You could turn that into meters in scientific notation. That would be 7.5 times 10 to the 5 meters. All right, that's the distance above the surface. We also know that we have the radius of the Earth, and that again is on our formula sheet, that bottom one under constants. We got 6.37 times 10 to the 6 meters. And then we have that total distance, R. Right, and that's the actual center-to-center distance that we have to use in our universal gravitational equation. So we know that the total distance from center to center is the radius of the Earth plus the distance of the satellite, which is adding those two together, giving us 7.12 times 10 to the 6 meters, or 7,000 kilometers from center of Earth to center of satellite. Now we are working with circular motion, right? This is going to be our principle of physics number 2, uniform circular motion. The net force acting on our satellite is equal to the mass of the satellite times its acceleration. And we know that the only force acting on it is the force of gravity. And the acceleration is only centripetal acceleration because we have a constant magnitude of our velocity. It's just changing its direction as it's orbiting around the Earth. So we're going to expand our force of gravity into our universal gravity equation. The force of gravity becomes gravitational constant times the mass of the Earth times the mass of the satellite. Call that M. Let's call it MS, mass of satellite. Mass of Earth, mass of satellite, over the total radius center to center, total distance between their centers squared, and that's going to equal the mass. In this case, we're analyzing our satellite's motion and the force on it. So this will be the mass of the satellite times the centripetal acceleration. But since the question's asking for the speed, break or expand our centripetal acceleration into speed squared over radius. And from here, we're going to want to solve for speed. So the equation we end up with for speed there, it's multi-step, right? We can see mass will cancel out. We're trying to solve for speed, so we'll multiply both sides by radius. That square goes away, and we're left with v squared is equal to g, mass of Earth, divided by r, and we need to take the square root of both of those. So the speed of our orbiting satellite is equal to the square root. Gravity constant is 6.67 times 10 to the negative 11. The mass of the Earth, I'm running out of room, is 5.98 times 10 to the 24. And our radius, which we calculated, our distance between centers was 7.12 times 10 to the 6. And that, when it is punched in our calculator, gives us a speed equal to 7.48 times 10 to the 3 meters per second. That's a 9 out of 4. 7.48 times 10 to the 3 meters per second is our tangential velocity, right? The velocity of our satellite. Orbital speed. All right, so whenever we're solving these, we gotta remember the only force acting on a satellite is the force of gravity, right? Which is going to be equal to the mass of a satellite times its centripetal acceleration. And we can either solve for speed using this, or we could also solve for period using 4 pi square r over t squared. All right. That's all for this unit. Good luck with the homework and your quiz.